Professor Chris Carothers giving us a nice lecture on this topic he's been working on for several years. And Chris is a professor in the Department of Computer Science, as you can see there, and he's our leading authority on high performance computing on campus. He's the director of the supercomputing center that we have, and he also teaches our parallel programming class. And so we're very happy to have him here. And so with that introduction, I'll let him proceed.
Hey, thanks so much, Joel. I really appreciate the introduction. And thanks for everybody for attending today's lecture. I do want to just give a quick pointer to a note that Joel sent out yesterday regarding STEM shutdown during this time. We're very much feeling the protests that are happening around the country in light of racism, and I just want to encourage everybody to attend that, and we will be, Joel will be, of course, leading that discussion. So Joel, thank you for taking that on. Now, with respect to the topic today, I'm going to tell you about parallel discrete event simulations, some work we've been doing there, and hopefully it will excite you to know that this particular application, you can scale it up to very large core counts. In this case, we've been able to go up to about 2 million cores. The software that this uses is called ROS, and so down there is a GitHub location for it. So without further ado, let me just, whoop, next slide. There it is, okay. So again, what's our motivation here? Why do we want to do these large scale parallel discrete event simulations? There's really two drivers for this. One, of course, large scale systems, and these could be, when I say systems, it could be human systems, it could be computer systems. There's just a broad range of things that one models with this particular approach. They're growing in complexity, very difficult to understand. The other thing, if I look on the math side of it, the analytical models tend to be very constrained. They tend to make assumptions about, say, distributions of events in these systems and things like that. And so with this, we end up with a large scale system. We can't model it necessarily purely mathematically. And so we need to apply a discrete event approach to this, which I'll talk to you more about exactly what I mean by that as we move forward. But again, when we run these type of models from serial to parallel, we're going to see a dramatic shrinkage of the execution time, which then has an enabling effect of turning something from sort of some back of the room, I can do this analysis thing, to being a sort of predictor of what if capabilities. And then this enables in turn the ability to begin to put this sort of in a real-time decision support loop potentially. So you can get results in hours, minutes, instead of days, weeks, months, or even years. And so it has a really profound implication here. Some examples of things we worked on or this technology has been used is in, for example, modeling the national airspace, modeling of all sorts of different networks. And of course, my interest has been modeling next generation supercomputer systems. So I just want to drive an example to be more specific about it. So this is actually, we did work on this problem when I did a faculty internship at GE, in fact. So you want to model distributing content over the internet, movies over the internet, something that we've been taking advantage of probably a lot these days. So if you have 4 million homes or 1 million homes wanting to download a 4 gigabyte HD movie, if we were to simulate this in some sense, how long would this take? If we assume a sequential simulator can go at about 200K events, you assume something like 8 hops per packet, which might be shorter. Some hops are much longer over the internet. And you've got 4 gigabytes, yielding something like 4 trillion 1K packets. You end up with something like a 32 trillion event simulation. This is just one simulation of this, by the way. If you do the math, it's something like 5 years of compute time. So not very reasonable to even think about doing it this way. So in this case, to address this, you can begin to look at, parallel simulation techniques to bring down that execution time. And there's a lot of other examples one can use for this as well, but this is sort of interesting driving one. So what we'll, for today, with that driving motivation example, we'll do sort of an intro, what I really mean by discrete event. Then we're going to talk about sort of these parallel discrete event, which we call abbreviated PDIS schemes. In particular, we're going to focus on one called time warp. And I'll talk about some optimizations we've done to that called reverse computation, which is going to sound weird as I'm saying it now, meaning why running backwards, because that's exactly what it is going to help me run faster forward, but we'll see how that works out. Then I'll talk about some of the systems we ran it on, particularly the Blue Gene supercomputers. And I'll talk about more why those systems are really important for high performance computing. Then I'll talk about our implementation of this, some observations in future directions. So if I look at just a core discrete event simulation, the core approach, it's actually fairly simple, right? The fundamental concepts are I have a state of some system. These are our state variables. And then I'm going to define a set of state transitions. And so then this discrete event computation can be viewed really as a sequence of these events, with each event computation assigned to a timestamp in the simulation. Ideally, it's unique, but it doesn't necessarily have to be. And so then each one of these event computations will effectively modify state happening at a particular point in time, as well as schedule new events into the system. And that's pretty much it at a high level. All right, so then we could do an example of this. Let's look at doing a discrete event simulation of an airport. We all haven't been flying that much these days, but we'll do this anyway. I think it'll still all have, we'll still feel the example. So essentially, if you're going to model air traffic at an airport, you'd have sort of three major events. They'd be an aircraft arrival, landing, and then departure. And in this sort of graph here that you're seeing, you can see the example of an arrival, landing, and departure events. What's interesting here is you're processing the arrival event schedules the landing event and so on and so forth. So you're seeing the actual causality of the events there. And so then under the covers in our, so above we have the model, under the covers, we're actually in the simulation engine, we're going to be storing all the unprocessed events in some pending event list, and ensuring that the events are going to be processed in what we call timestamp order. In fact, that's sort of the golden rule of these systems, is that we're going to largely strictly adhere toward guaranteeing we're going to process events in timestamp order, even though ultimately we're going to do it in parallel. So this is how we can begin to break apart, and you started seeing that a little bit in the picture, the discrete events, sort of discrete event simulation system. So at the top, we have the actual application. So that could be your airport model, for example. And then under the covers, again, we have this simulation executive. So essentially at the top level, at the application, we're worried about state variables, the actual code, the event code itself, right? That sort of affects system behavior. So all the state variables, whether a plane is landed or in the air, things like that, as well as any IO. Down below, it does all the event list management, and really the heart and soul of it is going to be the managing of time advance. So ensuring that we're, again, processing events in timestamp order. So here's an example, the sort of the event-oriented view, again, using our airport as an example. So again, at the simulation application level, we're going to have our state variables, as well as our event handling procedures. And so then putting more meat on the bones here, we begin to fill out some of this model that we're going to be constructing for the airport. So if the state variables are going to be sort of in the air, on the ground, runway free or not, which is a Boolean variable. So those could be the state variables for our airport. And then, of course, the event handling procedures themselves are the arrival event, landing event, and departure event. And so then again, under the covers, we have our event processing loop. And essentially the core of this event processing loop is ensuring that we're going to be processing events in timestamp order. So we're always removing the smallest event that we know about in our pending event list, which is over here. And and we'll remove that event and always be processing that. And in fact, that event, that smallest event in the system, whenever we're processing it, becomes what our notion is of now. So when you're processing one of those events, time now is whatever the event, the timestamp of the event you're currently processing. And then you invoke the handling procedure above in the simulation executive. So that sort of gives you a feel for how this would be structured between the simulation application and executive. So now we can delve into the specific particulars of the model. I sort of started this a bit already. So if we were to really delve down and create our own air traffic model here, and again, this would be very simplistic, we could start off with defining some constants, which would be first the R, which would be our time on the runway. So this would be the amount of time we're going to spend on the runway. And G is the time we're going to spend on the ground. So these could be constants. Another thing they could have been is a distribution, but for simplicity, we're going to say that they're going to be constants. The other thing is the state variables now. So each airport has these variables, and for now we're keeping it simple. We're going to have one airport, but you could imagine having a network of many airports, each of those airports having a different complete set of state variables. So these state variables would be currently the not time now, which would be the current simulation time. There's in the air, which is the number of aircraft, landing or waiting to land. There's on the ground, the number of aircraft that have officially landed, and then if the runway is free or not. And we're also making an assumption here, each airport only has one runway. Obviously, airports typically have more than that, which you could extend the model to do that if you wanted to. In terms of modeling the actual events themselves, again, we have the arrival, landing, and departure event. So we can begin to just look at our sort of pseudo code for this model. So again, we've got our constant variables as well as the other state variables that we're working with here defined above. And so then this is the code for actually processing an event that denotes the arrival of an aircraft at our particular airport that we're modeling. So the first thing we notice is we increment the in the air variable. So, and that's a key thing to note is that in discrete event simulation, there tends to be a lot of increment and decrement of statistics of these state variables. And I'm sort of saying this now as foreshadowing against when we think about running things in parallel, we're going to leverage that idea, the fact that a lot of state variables tend to be increment a statistic of packet losses in a network or something like that. They tend to be very tend to have that type of structure to them. All right, so we increment our in the air variable. Then we say if the runway is free, we go ahead and then reset it to being false, set that Boolean variable to false now because we know we're going to be scheduling an event in the future that's going to occupy the runway. And so we're saying there's going to be a landing event at time now plus the time it takes for each aircraft to land. So we're scheduling an event into the future at time now plus the variable R. One thing to notice is other arrivals coming behind this event. If the runway isn't free, you note that the landing event isn't going to be scheduled then. What's going to be interesting about this model, as we'll see, is that the actual landing event will then allow the next plane to land behind it. We're not so concerned about which plane, it's just there is a plane. And so we don't get into the particulars of which plane is landing or not in this particular model. So this is the landing event. So here we see we're going to decrement. We're going to pull one of the aircraft out of the air. So in the air actually is decremented as opposed to being incremented like it was in the other. Except this time we increment the on the ground variable. So again we see this increment decrement type of structure. Then we're going to go ahead and let the landing events for this. Now that the plane is actually landed at the airport, we're going to schedule into the future at time now plus G. So, but in fact, time now is really the previous time now plus R that we were just at. But so it'll be at time now plus the ground time. So that's the time we're on the ground. And so we'll be scheduling that departure event in the future. then here's where we actually then schedule the next landing event, you'll note. So if in the air is greater than 0, we'll schedule the landing event at time now plus r. So we know that the runway is still going to be busy, but we're going to hold it busy if there's something else in the air to come down. And so that's what that logic's doing there. We're scheduling it for now plus r. Otherwise, if that wasn't true, if this was the last plane, we pulled it out and in the air became 0, then we're going to reset the one runway free so that in fact instead of the landing event scheduled the next landing event, the arrival event will do it for us. So one or the other. And this sort of gets into a subtle piece in discrete event models, which we have to make sure that the event population in the models that we're creating are relatively stable. And what I mean by stable is that you can't develop a model where, for example, every event results in the scheduling of 2 additional events. That would be unsustainable. Eventually, you would literally run out of memory because you'd have a doubling of the event population continuously upon processing every event. It would slowly but surely double in the system. So it's very important that when you're developing these models, you have an eye toward making sure that the event population doesn't grow unsustainably. So, and finally, the departure event, if you see what's great about it, and it's part of this stability point that I was making earlier, it doesn't actually schedule any events. It just, the processing of this event just takes the plane off the ground and decrements it, so we don't have any more planes on the ground, and then that's good. So it's as if the plane, goes off to another airport per se. In fact, what happens is the event population in this case, it's absorbing event, but it's not creating a new event in the system. All right, so this gives a sense of the timeline, so you can see sort of rolling forward how this gets rolled out. So we can have arrival of a couple planes at time 0. They get processed, or we see an arrival at time 1 and a landing event currently in the pending event list. And then at time 3, we see that arrival event that was processed. There's still a landing event there. Time 4 has a landing event and then a departure event. And again, I'm looking right here in the graph time now 4. So you can see we've processed the landing of F1. We still have these couple of events to process. So then the next one is at time 7, the landing of F2, and so on and so forth. So you're seeing that whole progression. And above, you can see how the variables actually change, the state variables change with respect to time. Where the runway was true, then it was held false for a very long time because we had a bunch of events that were being landed. Finally, once we processed them all, then the runway became free and returned to being true in that case. All right. So again, the summary here is, right, again, these discrete event computations are really kind of 2 major pieces. We can modify our state variables and schedule new events. So with that, we can divide a sort of a 2-tier system, which has the model at the top level, your application, and then the simulation executive. Under the covers, of course, we need some core data structures. In particular, we have to have a pending event list to hold unprocessed events in the system, which I'll talk a little bit more about. At the top level in your application, you have your state variables as well. And then the actual code itself, you have sort of a main event processing loop in your event scheduler. You'll have sort of handoff functions that call the application level as your event procedures. And again, the core of all of this is that we want to ensure that we process events absolutely in timestamp order. So that's the main thing. All right. So now so with that sort of introduction, right, let's talk about how we would begin to think about processing this in parallel. And so this first slide speaks to that. And the first thing you might think about is I could have a collection of processors on the x-axis, so processing element 1 to 3, and virtual time or simulated time on the y-axis, and we would just do a barrier synchronization, right? We could just do, for those of you, I think you've had some MPI tutorials already, so you could just do a bunch of MPI barriers after processing events. And so we could, in lockstep, execute this barrier across at each sort of time in the system. The airport example, that actually might work okay because we have constant timestamps, but the reality for discrete event is that that usually isn't the case. They're usually distributions, random number generation applied to this. And so time events occur at all sorts of different times on every processing element. And so then we really need a synchronization approach that is going to allow for sparse, irregularly scheduled event computations. They could be sort of anywhere in the virtual timeline. And so here we're seeing on the right panel there, this fact that it's very sparse, where PE1 and PE3 might have work to be done, but PE2 doesn't. And the next time, maybe only PE1 has stuff to do at that particular point in virtual time. And so then if we just sort of imagine that we just didn't synchronize everything at every time step, but just let things roll free, what would happen? And so we would immediately incur a problem that we call sort of events arriving in the past, which is a bad thing because, again, we don't want that to happen because our sort of golden rule in discrete event processing is that all events have to be processed in timestamp order. So how do we sort of deal with this problem? And sort of the solution that was come up with actually in 1985 or so was called time warp by David Jefferson. And so this time warp sort of mechanism can be really seen as in two different chunks, if you will, or two different parts. There is a local control mechanism and a global control mechanism. And you'll notice in this depiction, we still have virtual time on the y-axis, but we've changed from processing elements to these things called LPs, or logical processes. A logical process is really just an element or sort of an entity within your model that has sort of a separate set of state and events that are being processed. You can have one or more LPs per core or processing element in the system. But LPs are the way we tend to think about these parallel discrete event systems. So we have a collection of logical processes, and they're going to schedule events into the future as part of their event processing. And again, we still have this problem with events arriving in the past. And so to deal with that, we have this local control mechanism and global control mechanism. So the local control mechanism does exactly that, the error detection and rollback, which will say what the rollback component here is. So for example, LP1 is sending an event in the past of LP2. And so then what has to happen? Well, we've got to clean that up now, right? It's arrived in the past, and because LP2 has progressed in virtual time beyond that point in time, we actually need to roll that event back. And by rolling it back, we're going to undo any of those state changes. So modification of state, as well as we have to, and this is where it gets a little more crazy for time warp, we have to cancel any sent events that we scheduled in the system. So we have to go after this other event that we just sent, might be unprocessed on the other system, but we've got to go kill it off and erase its existence because it's been incorrectly scheduled because this event, it was incorrectly processed in time. So we've got to clean all that up effectively. So that's the first step. So to do these state changes, we actually have to record all the event computations that we're doing as we're going forward, but we need an ability to actually begin to reclaim this. We can roll them back, but we can't let them persist forever because by being able to undo these state changes, it implies that we're going to be keeping that event processing around for some period of time. But we need a way of reclaiming that. And that's what the global control mechanism is going to do for us. It defines what we call global virtual time of the system. And you can think about it as the smallest unprocessed or partially processed event in the system. And we know that that's a time beyond which we'll never need to roll back. We know that that is the smallest event in the system. And so there's no reason to roll that back. So we can declare that as the global virtual time. And then any event that's been processed that's at a timestamp lower than that smallest event in the system, it's safe to sort of collect that event, and we call it fossil collection or garbage collect. And then we can reuse those events for future event schedulings. And so that's sort of the nature of the time warp mechanism. All right, so again, that sounds expensive, right? We've got this rollback mechanism. We've got all this state saving happening potentially. Sounds expensive. Can we do something else? There are non-rollback options, and we call those conservative because they disallow any out of order event computation or execution. Examples are deadlock or sort of classes or deadlock avoidance. So you try to avoid any deadlock in the system. We'll see actually how that's easy to achieve and that you have to avoid it. And the cornerstone of that one is the null message algorithm. There's also a sort of a similar one to time warp. It's deadlock detection and recovery. So it's sort of like the time warp local control mechanism of detecting rollback in the global and GVT. They have some analogies there, but essentially they don't allow any out of order event executions. So here's the null message algorithm, and essentially it's just like your sequential algorithm that you would see running on a core, except there's this added part here in sort of blue-green where you're having to send null messages to all your neighboring LPs, and you do that with a timestamp indicating some lower bound on future messages that you might send. In other words, you're having to send promise times that you're saying, I will never send an event to you at a timestamp less than this. You're sending a promise time into the future. And you're doing this for every event. This was actually one of the original parallel discrete event algorithms. And you can see that it's very costly because of these null messages that have to be sent. In fact, the other subtle piece is send null messages to neighboring LPs. This implies also in your model that you have some sense who your neighboring LPs are, meaning every LP you would be communicating with. So you have to know that sort of ahead of time, and that might not be possible for all your models. The other subtle thing here is I'm sending it, indicating a lower bound. We'll see later that that lower bound better not be zero, because if it's zero, there are some problems that can happen. In particular, you just don't have a lot of events that you can process at any one time because of that. So there's another problem called time creep, which is, and this is sort of, again, using the airport as an example, where if your minimum delay, say in your model, and let's say we're minimum delay between airports, is very small relative to the average timestamp increment that you're seeing, you can have to send a lot of these null messages going through the system. So we'll kind of scroll through this quickly, but essentially you see that we had to send something like 5 null messages in this example to process just a single event. So again, in this specific case, instead of having 3 time units as the minimum delay, we said it was half a time unit. Yet the regular events were scheduled at much greater times than that. And so we had to send all of those null messages to figure out what event was safe to process in the system. And we had to go several times around incrementing things before we finally figured out, because we started off at a small initial time of 5. And so to get to the event at 7, that was the smallest, it took a while to go several rounds around this to figure out what was the smallest event in the system. So there is this time creep problem. Um, then there could be a live lock, and this is what I was alluding to earlier. If your minimum delay is 0, so in other words, if you had a distribution, let's say the exponential distribution is a great example, which could generate a close to 0 or a 0 timestamp increment, then you could see some sort of live lock in the system where I'm sending time now plus 0, 0, 0, and it goes on forever, and no LP can advance. Essentially, what you end up needing to do here is practically calculate a global virtual time, and then figuring out that ORD has the smallest event in the system at 7, and then you can move forward. But otherwise, without having that, you wouldn't be able to advance simulation time. So this gets into this idea, this sort of minimum timestamp into the future we call a look ahead. And essentially, there's look ahead has some constraint on an LP's behavior. One example we call link look ahead. This is more in networking, that we're kind of saying that the link in between 2 networking elements has to have some minimal time or delay along that channel, if you will. And so any message sent from time now must have that time now plus the link delay included on it. The interesting thing about this notion of embedding time as part of your synchronization for your model is, let's suppose you run a new model and the look ahead or the link delay shrinks. So if I get a faster network, or I have faster communications, or some other artifact of your model changes the embedded sort of time advanced mechanism that you're using, guess what? Your performance could diminish and diminish greatly. We'll see some examples of that as we go forward here. So this is just some examples of 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 the impact and sort of what I was alluding to earlier about how look ahead is clearly dependent on your simulation model. And so then that will have a profound, again, implication in terms of the parallel performance that you're able to get out of this. So again, the bottom line here is look ahead changes as an LP topology changes. Again, that's going to also have an impact as well. So the LPs to which you communicate with within your simulation model, that will have an impact as well. So we're seeing that while we can run conservatively and not have to worry about the problems that time warp was introduced, there's some complexities here that make time warp begin to look a little more attractive, largely because you keep changing your model, you may change your parallel performance in quite significantly. So here's an example of that with a look ahead. So we see what's possible without look ahead and what's possible with look ahead. So you're seeing here, there's no events that can be processed. But if I add just a little bit of look ahead, all of these events come into focus that I'm able to process in parallel. So A, B, C, and D across those LPs. And so by having that look ahead into the future, we're able to make better, more efficient parallel processing. What's interesting about time warp is we'll see it doesn't care about that. You can actually have 0 or near 0 look ahead in your system, and it doesn't particularly care about that in terms of its synchronization. So here's what happens if you were looking at potential for speed up on, say, up to 16 processors. And so we can see if I have a large sort of look ahead, this is a look ahead ratio amount. So it's actually called the inverse look ahead ratio, where you take look ahead divided by the average timestamp. So if I have a model with essentially a lot of look ahead relative to the average timestamp increment, you're going to get pretty good performance. But then if you have lower amounts of look ahead, again, relative to the average timestamp increment, you'll see your performance shrink, and you'll kind of get, places where it doesn't even make sense possibly to run the model in parallel. So again, takeaway message here: conservative algorithms live and die by their look ahead. Another option is, of course, deadlock recovery and detection. So again, the idea here is that we're going to ensure we're going to process events in timestamp order, but then we have to have a mechanism that's going to detect any sort of deadlock, right? As we're removing the smallest event from all of the FIFO. So we have to wait, and this is the key part in this algorithm. We're waiting until each of our LP neighbors has sent us at least one message or promise time, and then if we're all waiting, then there's a problem and we can all deadlock. So we have to detect the deadlock and then sort of do a recovery from it. So again, we have to figure out what events are safe. And again, this is that example we used before where we were in live lock or a deadlock. So then we just can compute effectively what you end up doing is computing a global virtual time, and you can identify what events are safe to process. Once you have your global virtual time, for example, that it'd be safe to process event 7, but that would probably be about it. With the assumption of a 0.5 timestamp increment. But when we go to a 0.3, if we increment our minimum delay or our look ahead to 3, then we see that 8 and 9 are also safe, and 10 is actually okay if we're going to allow same time events to be processed in any order if we make that that rule. So this is the deadlock recovery. Again, this looks very similar to global virtual time in its calculation. There's ability, again, to prevent creep. What's interesting, the way to prevent creep is you end up computing a global virtual time as well. And so you can sort of show that by jumping in and doing that calculation, you can sort of avoid the creep problem and jump ahead in time, if you will. And so you're not immediately just advancing to by your own look ahead increments, but instead you're able to jump ahead to when the next event is and save all of those null messages. So the big summary here is that there's just no free lunch when it comes to parallel discrete event simulation. Of course, time warp has its state saving overheads. We saw null message has the creep problem. We can't have zero look ahead cycles. That causes problems. The ultimate look ahead is actually essential for any sort of concurrent processing. If you make any changes to your program, you can have a large impact on your parallel performance. And then, of course, deadlock detection recovery, we're seeing here that you ultimately need a GVT algorithm anyway, effectively, some notion of the smallest timestamp of the system to be safe to process. But it requires work to sort of figure out what events are safe and not safe. So, there's a lot of these complexities here. And the question is, can we avoid some of them? And in particular, we wanted to focus on, well, can we avoid some of the state saving overheads, if you will, for time warp itself? And so this jumps into the topic of reverse computation. So again, to avoid these state saving overheads, we came up with the idea some years ago, in fact, to think about if we could, instead of do state saving, we could automatically generate the backwards code or reverse code from the model source that reverse event code would actually effectively undo the state changes that the forward code did. Our reason for wanting to do this is we were thinking we could get better performance than strict just full-on state saving of the logical process. So all of those state variables on every event have to be saved someplace. And so if we had a undo function for every forward function, we could potentially lower the overheads of the forward computation and significantly reduce memory overheads. And so this was our original idea. We could have some compiler, which we do have an initial version of one that does some of this, where it takes your original code, modifies it, and inserts the reverse code. And again, this reverse code is going to do that undo operation for us. So here's just an interesting example where we're having a simple network switch where we have an original rival coming into the switch, and we're saying if the queue length is less than the size of our overall buffer, then we'll go ahead and stick it in. Otherwise, the packet's going to be lost. And just like I was alluding to earlier, we see in these models, and we see this over and over again, that there's a lot of these increment and decrement type operations to state variables in discrete event models. So again, network switches, we saw that in the airport. So this becomes sort of interesting. The forward case, we just have to sort of increment or sort of instrument what path, which if else we actually took. So we introduced a bit variable here, B1, and we'll say if I took the if part of the loop, we'll say I take set that to 1, otherwise it'll be set to 0. So we're recording what control path within the forward event handler we actually took. Everything else remains the same, and then the reverse path just says, oh, depending which path you took for the event when you process the event, and this bit variable is stored with the event itself, by the way, that is stored internally to the event, we'll know which path upon rolling it back we need to take. So if it's B1, we actually do the reverse in reverse order. So of the delays, we'll decrement the delays and then decrement the queue length. Otherwise, we'll decrement the loss variable. We also note that all of these are integer variables we're dealing with here, which is very common also with discrete event models. So again, the benefits of this reverse computation are we're not saving the whole, normally you save the whole state of the LP, which could be the whole buffer of this network that we were talking about. So if it was set to 100, we'd see 100x reduction in state saving. And the other thing is we've transitioned the overhead. So we were seeing forward computation always incurring these state saving overheads. So we've sort of pushed those overheads back to the rollback phase. And rollback is a much rarer thing, or it should be in practice. We typically see well over 90% efficiency rates. So rollback is actually a much more rare thing than the forward computation. And so then we're going to see dramatic increases in speed, as well as the amount of memory the model takes, so we can run much larger models in the same amount of memory. So how is this all possible? Again, the big trick is that we're observing that, again, most of these operations are plus, plus, minus, minus, and we call that constructive. So essentially that we can recreate the state from the previous operation. There's also destructive operations, which we'll talk about, where you can't directly recreate that, and we'll sort of talk about how we can deal with that. The big gain here is that the control state of your model typically is significantly smaller than your data state, and so we can record the control state and not the data state of your model. The other interesting thing is it turned out there are perfectly reversible high-level operations that if you look at the individual operations, they might not be reversible. And one key example is random number generation, which we'll talk about. This is just an eye chart which shows all the rules that we created for how you do the reversal and when and what it requires. The big one is, of course, a destructive assignment operation. So essentially, destructive assignment revolves into just recording what values were changed, and there's nothing we can do about that. So we do have, and this is what I was saying, destructive assignment. That's one. Another one is a while loop, any sort of while loop with an if in it. That one becomes a problem because you're recording which path you took in each and every iteration of the while loop, meaning which part of the if statement you took inside that while loop. That's a problem. But other than those, we do find we get a lot of mileage out of using reverse computation. And so these are just the general rules for applying that. We've actually done an example of this with a compiler to help generate the code for you, but we find we're still at a stage at this point, a lot of folks, we do handwriting of these reverse event handlers, but we're fairly successful at it. We've gotten quite good at it, and it's not as terrible as it sounds at first pass. So again, destructive assignment, that's a problem. But it turns out if we look at higher levels, we can begin to kind of figure out, well, we might be able to get around some of this. And in particular, one to look at is random number generation. So for example, if I look at the code for random number generation, this is the actual generator we use as a combined linear congruential. I know in physics, probably the most popular one is MT19937. That one actually, in talking to the authors some time ago, they thought it's reversible as well. But anyway, this is the code that it uses, and it looks pretty intense. Obviously, a lot of destructive assignments. You see a lot of just setting of variables k equal to this value, and so it doesn't immediately look like this is going to be successfully reversible, except if we look at the math, it turns out it is. In this type of generator, again, it's a combined linear congruential. So it's based off the following recurrence above, where I've got some seed variables, seed values, x sub I sub n, where n is the nth of the generator. And all we're doing is we're taking the seed value that we start with, multiply it times this a value, which a is the primitive root of m sub I, where m is in fact one of the 4 largest primes that actually fit, prime values that fit within 32 bits for this particular generator. So we take a sub I times this seed value we have 4 of these seeds to get the generator up to 128 bits. We modulo that times m sub I. So that's the core of the generator. Turns out, again, some cool number theory math says that we can define what's called the inverse of a sub I modulo I. So this B value, all that does literally is run the generator back one step. So instead of circulating the period of the random number generator in a forward arc, we're simulating it in the reverse arc. It does get a little interesting in the math because we're taking the primitive root, or sorry, the a sub I, the primitive root, to the power of m sub I minus 2. Again, there's some cool number theory there that will allow you to do that calculation pretty quickly without blowing through 32 or 64 bits of representation. But once you've done this calculation, once the B value, you can run the generator literally backwards around the arc. So you can go forward one step or backwards one step, and it's done. So we can do it without any state saving is what's cool. All that we have to do is figure out what the B sub I value is, and we can run the generator backwards. So very, very neat. And then all of our distributions can run backwards as well because of this. We just have to remember how many calls that we took to the random number generator, and we're good. We can just make sure in the reverse code we do that. We make those reverse calls to the generator and get it back to its state. And it does work very well. So again, this reversibility tends to be very efficient. And I guess the big message is it tends to be very well suited for, again, small event grain models. So models such as a lot of networking models where you're just in-queuing packets or things like that. Folks are also looking at it in terms of using it for kinetic Monte Carlo as well. So I know there's a lot of physics folks on this talk. So kinetic Monte Carlo is a very popular method there. You can use a reverse computation discrete event approach for that method as well. And folks at Lawrence Livermore have seen some success with it. So again, in terms of the applications that we've seen for this beyond the one I mentioned before, kinetic Monte Carlo, we've seen wireless telephones, large-scale internet. We've been working a lot with HPC network models. Folks have looked at neuron models, the Hodgkin-Huxley models. We've been looking at neuromorphic computing with it, as well as other circuit simulations. Folks have done plasma physics models using a sort of a particle and cell approach, but a discrete event as well. So a lot of different applications you can apply with this technique, as well as there have also been some interesting non-PDES sort of desires as well. So very applicable to a wide range of PDES and even some non-PDES models. All right, so from there I wanted to shift to the systems that we're running on, which was at the time the L, P, and Q systems. And I want to emphasize that these systems actually hold, I think now, a particular place within high performance computing as possibly being some of the most scalable systems really ever created to date. And we'll begin to talk a little why. And then from there, we'll talk about how we did our implementation and some performance results. So this was the Blue Gene L system. It started off in 1999. We actually got our first Blue Gene L at the CCI back in 2007. Not a very fast system. These processors were only around 700 megahertz. There were 2 of those cores per node. The P system gets a little faster with 850 megahertz. And again, they were slower cores, but they were extremely power efficient for their time, which made them very attractive for large scale high performance computing. But the big secret to these systems was their networking. And that was true for L, P, and Q, as we'll see. In particular, they had a torus network that was just for point-to-point messages, so for MPI point-to-point messages in particular, but they also had barrier, collective, and I/O networks as well that were dedicated. The great thing about these systems across all the generations is that they were very well balanced between the network and the processing speed. Unfortunately, today, we've probably seen with the GPU machines, the balance is kind of weighted more toward compute. And the networks now are a bit underpowered for the compute capabilities of these systems. But I think that in the future, that's going to switch back again. We're going to see newer systems that are more Blue Gene network-like in the coming exascale era. And the other key pieces there is exceptionally what we call low jitter, meaning for all intents and purposes, you run your application on a Blue Gene, you run it once, you get runtime, you run it again, you're going to get the same runtime. You're going to see very little variation in the runtime of your application from end to end. So it was very predictable in this regard. This just sort of shows you the scale out of the system. One observation I wanted to make with this is if you look at a rack here in the middle of a Blue Gene L, it came in at around 5.6 teraflops. To give you a sense of where we are today, we've compressed all of this compute power from a floating point perspective into a single Volta GPU, to put it in perspective. We don't have quite the RAM. We have 32 gigabytes on a single Volta GPU from 512, but this has all been compressed. And this really gives you a sense of where we've come today on the system. But again, the networking of this system and these other Blue Genes really stand out historically, and I think going through in the future as a way to build systems where you can run a single application that scales to the whole system. And we'll talk more about that. This was the P layout as well. So you have single chips on cards going into drawers, getting into the racks, and you could have relatively large systems for their time frame up to a petaflop for the P system. And then finally we get to this then compares them. And again, one of the big things that made these systems really just impressive is the actual collective network capability. So if you're doing any sort of MPI, all reduce, or any all-to-all operations, any of those collective operations, you could do a collective across the whole system in just a few microseconds. And that held through even to Blue Gene Q. And this is really where they made their impact known, is this sort of collective, because you didn't see the slowdown in codes that made use of collectives, which of course, for our time warp, our raw system that we'll be talking about, collectives are the way that we do the GVT calculation. And so by having the super fast collective, it made the application inherently scalable, along with very fast point-to-point messages as well. Blue Gene Q really changed the game in the sense that it gave more functionality, but much improved performance. And we saw scaling in terms of number of MPI ranks beyond which we could even achieve on Blue Gene L or Q, and we'll talk a bit about that. But in particular, we had more memory per node, so we went up to 16 gigabytes, which was very important. The Blue Genes in previous generations were known for maybe not having enough memory per node. The memory bandwidth was actually pretty good, but the main point that actually happened with these systems, and this is another point where we got super linear performance, which I'll talk more about, is there was 32 megabytes of cache running at over half a terabyte a second. And if you took a rack of one of these systems, that meant you got 1,024 nodes, so you'd have 32 gigabytes of L2 cache. So you know, for an application, if it fit more and more and more in cache, you could get tremendous performance boosts, and you would actually could see super linear performance. The other part that they did is they isolated the operating system to the 18th core on every one of these nodes. And so that actually reduced any sort of application jitter. The operating system didn't interfere with your application. The torus network, you had complete control of the part of the torus that you ran over for your job. So you didn't see any job interference like we see on some of the systems today. And so you got, again, very good predictable run times. In terms of a rack of Blue Gene Q, you could have 1,024 nodes or 16 3D4 cores, and you could fully occupy all the cores. And the cores actually were hyper-threaded, and so you could have up to 65,000 MPI tasks running on a single rack, and then scale that out across racks. So a very scalable architecture, one that we haven't seen for a while, but it will probably come back in some of, again, these future exascale systems that we'll be seeing. So the system that we were able to run on, which we'll talk about a little later, was Sequoia and Super Sequoia, we called. So Sequoia had 96 racks of Blue Gene Q, which gave you something like 1.5 million cores of the A2 processor running at 1.6 gigahertz. Again, it was around a 16 petaflop system, but that jumped to the 120 rack system. So they combined two systems together and got 120 racks for a short time, which scaled the number of cores out to nearly 2 million. So it's 1.966 million. One thing that was interesting in this is the way this torus was laid out. It was a 5-dimensional torus. And so you can see when they laid out the two torus networks, the 96 rack one was fairly even in all the dimensions, except for the last one, but that was by design. Whereas this first dimension grew, and that was just the way they could put it together. The consequence of that is that the what they call it bisection bandwidth. If you chop the machine in half, it actually didn't grow. We were actually worried about that, but it turns out that that we were worried about scaling of the code, but it turns out that that really wasn't a problem. The performance still continued to increase even on Super Sequoia, and we'll tell you more about that. Just do a quick time check. All right, so implementation. So again, I know you've had the MPI part of the tutorials. So the way that we implemented ROS is it's largely using MPI iSend and iReceive. So it's very carefully orchestrated. In fact, we have a whole message passing layer that does this for us, where we're constantly having messages posted to the system, and we manage that memory and events very closely. So we have a pool of network events that we use for that. The other thing is that we allocate both the event and network memory pools at startup. The other thing, and this is was an interesting addition, is so we've got these anti-messages that we had to trace down, and we talked about very early on. So it turns out that we had to store positive messages sent across processors in what's called an AVL tree, a data structure, so that we could quickly look up an anti-message for its positive message and do that match and actually do the event cancellation, as opposed to sort through all the events in the system for doing that. In terms of the pending event list, we use what's called a splay tree, which was very fast at keeping all the lists sorted. Splay tree was used, it does a great job at keeping what's the next event to process at the very top, but it's not good for searching. But the AVL tree was better for searching, so that's why we had the two different data structures. The other interesting thing is we had to go to sort of computed LP to core tables and not use sort of static data structures, because we were talking about running models with hundreds of millions, if not millions of logic or billions of logical processes. And so that wasn't scalable either in terms of the memory. So we had to have computable mapping tables. Again, in terms of the global calculation, we actually, to implement GVT, we have to do an all reduce. So the GVT algorithm is actually kicked off by each core recording number of sent and number of received messages. This is in the MPI layer. We'll try to receive all the MPI messages that we can get. We'll do an all reduce sum on sent minus receive, and it better be 0. If it isn't, we've got to do this again, because it means we've got some message left in the system. But once that's done, we can then have all the cores figure out what their lower bound timestamp is, LVT, based on what's the smallest processed event from their perspective. So every core of the system does this, and then we'll do another all reduce across all those LVTs, and that becomes the new GVT. So again, collective operations are incredibly important in making and having them scalable on the Blue Gene system. Really improve the performance. So again, how does this sort of translate to Blue Gene systems? So we did a couple of different performance results or models. One was a synthetic benchmark that we call p-hold, and we'll do a couple different versions of this, but essentially it's a pathological benchmark model that randomly can send messages to any LPs in the system based on some remote percentage. There's an initial events in the system, but it's really quite pathological and hard to get good parallel performance with. Definitely scalable parallel performance. And in particular, it's an exponential time distribution with a mean of 1. So it means a look ahead of 0 is possible with this model. So it's, again, very hard to get to run in parallel fashion. The other one was a cellular telephone network model, an in-by-in grid model where essentially cell phone calls are made, and we have call arrivals and call departures in a grid space. And so essentially you have folks are receiving and sending calls, and they're walking around this sort of 2D grid space, and we're measuring sort of when you're allowed to make a call and when you can't because you've oversubscribed cell phone services in a particular region. All right, so we'll just start diving into some of the results. The big thing we saw, at least in terms of the Blue Gene L, is we were getting into the billion event rate, which we'd never seen before. So this was an amazing result, and this was for 10% remote on the p-hold benchmark I was talking about. And even more impressive is if we went to 100% remote, meaning every event was being scheduled to a different processing core on the system, we would see scalable results going across the system all the way up, and we got 2.7 billion as well. So we see really stable performance across the system, and we just really hadn't seen that before. And again, this is attributed to the Blue Gene L's low noise jitter. It was just very reliable in this regard. If we jump to the, this was on 128K, so this was up to 128 on Blue Gene. I think that's L. Sorry, my top of the slide is being hidden by one of the things. So this is, I'm almost certain, L. This was out to 128K processors on Blue Gene P, the next one, where we got to see 12 billion events per second, which was also amazing, and out to this many cores. And so we could actually start seeing falling over of the event rate as we went to a bit further. Again, we just didn't have enough work to be done at this level. So we're starting to see the event rate fall over and rollbacks ensue. We'll actually see this in a graph here where we're seeing nearly like 99, 98% as we get to 64K processors, and then it falls off. It just, the efficiency falls off extensively across all the different configurations. And so again, rollback efficiency is defined as 1 minus the events rolled back divided by the net events processed. So it's this 1 minus that is the rollback efficiency. It's defined that way, not just in terms of, in other words, not in just terms of total events, because we were seeing that the rollback efficiency, if it was 80%, would actually be not very good performance if we define it as events rolled back relative to total. But if we just use net events, then that became a better measure, and the efficiency versus performance were more in line. This is on the PCS application. So if we went out to 32K cores, we were seeing up to 2.5 billion events per second. So again, tremendous performance improvement. We saw it was beginning to tip over here, but again, we were getting to the edge of what we could do in terms of the size of the model that we were simulating in this particular case. So this gives you a feel for where the rollbacks were being done as well. So frequency of rollbacks. And this is as a percentage of committed events. Again, very low percentages. This is for the PCS model, like 5% rollbacks at the worst, 1% for secondary. The difference between secondary and primary are a primary rollback's caused by a straggler, meaning an actual real late event arriving and causing a rollback. A secondary rollback is where you're canceling a previously scheduled event. It got processed on that processor. And so that cancellation causes you need to roll back that logical process. So again, we're seeing very few secondary and primary rollbacks, and ultimately that's a very good thing. All right, so now I want to jump into the results we got when we jumped onto the Sequoia system I alluded to earlier, and this was work that was done with David Jefferson and Peter Barnes out at Livermore. We modified the p-hold configuration just a bit. We had to scale it up a bit. And this is where I was saying we were trying to get, again, it's this pathological benchmark, but we needed to get to around 250 million LPs so that we could kind of keep us consistent 40 LPs per MPI task when we were going to run all the way out on the system. We were ultimately doing a scaling study. And then I wasn't able to run on this machine. It was actually a classified machine. And so I didn't know the fact that they were going to be able to run it at 128 racks. And this is the configuration it does. So we were running like something like 7.8 million MPI ranks with 32 of those LPs per MPI task. So with 16 initial events per LP. And so we'll see some of these results. And this was just the first set of results we got back in January of 2013 when the system was first coming up. What we're seeing is just tremendous scaling. So we're seeing the fact that if I run this on one rack using this many 16K cores, so on and so forth, you're seeing something like an execution time of almost 15,000 seconds. But we turn that as we scale up to 48 racks into 200 seconds, and we're seeing somewhere around 163 billion events per second in this case, so 164 almost, from 1 to 48 rack scaling. So that was just a tremendous performance improvement in scaling that we just had never seen. You can see even the efficiency. The other interesting thing is the net events processed is to the event. It's 32 trillion, almost 33 trillion events and change, but it's deterministic. There's no out of order. There's nothing that isn't processed in the same order across the system. So despite the scaling, we're seeing this consistent ordering of events in the system, which is also part of the software, but also the hardware as well. So we were very excited in the beginning seeing this result, but we were beginning to feel some intense frustration because we could not get the full machine results at the time. There was some low-level system stuff happening in the message layer, and we couldn't get jobs. Nobody could get a job to scale more than 48 racks. We were, in fact, one of the few folks that ever ran larger than even 48. And so we had to wait for IBM to fix the problem, and our time was short. They were getting ready to tear the machine back apart. And so, but we were able to finally get it. And these were the results we got. So we were able to scale beyond 48. We took the same model, that p-hole pathological benchmark, and it scaled from 48 to 96, and finally the full machine, 128. And you might not appreciate this, but I can say for our center as well, modern clusters to have something like 2 million cores available and all up and all running at the same time is nearly an impossibility today. Nobody in the top 500 of, if you look at the top 10 machines, has 100% of their machine available. To have the Blue Gene Cube be able to do that is just a phenomenal feat of engineering, and we just typically don't see that today. So essentially, we did get the run. We saw actually a performance improvement because of what IBM fixed. So we got 10% better performance at 2 racks, and so we started scaling from 2 racks, all the way out to 120 racks. Again, the peak performance was something like 504 billion events per second, and we were 93% efficient. So we went from 99.9 and scaled. The downscaling was only 93%, and we went from 6,300 seconds down to 65 seconds. So essentially, time for you to go get coffee. I can say the boot time for these jobs was, in fact, in this case, longer because of the way to set up these jobs actually took longer than the actual run in that case. But again, the scaling was just actually tremendous. And when we look at this, scaling it out, it was actually super linear, as I was alluding to earlier. We got 97 times speed up for only 60x more hardware. And again, this gets back to the fact with this strong scaling result, we were only running at 120 racks. We were only using about 65 megabytes of the 16 gigabytes of memory available in the system. There's a relatively small model on a per node basis. And so we were fitting most of that within that L3 cache. And so we were getting a tremendous performance benefit from that. And so till this day, we've not seen better performance than 500 billion events per second, even on the modern supercomputers of today, going forward. So if we look at the history of this one benchmark's performance over time, we've seen tremendous scaling through 2013, and this is sort of the last result. The latest generation machines are more what we call capacity machines than capability machines, although the next generation of exascale machines will be out, and so we're expecting to see us to resume this and hopefully get better results of these going out in the future. So if I come back to the original part of the talk, movies over the internet revisited, right? If we take this billion event capability that billion event per second capability, we can basically turn this same 1 million home, 4 gigabyte download movie that was 32 trillion events. It was going to take 5 years to calculate. We've reduced that down to only about 4 hours or 5 hours. That's a tremendous time compression. And that's really what massively parallel discrete event simulation can do for you. I realize that this model might be a bit simplistic in this case, but we've seen this in other modeling areas as well. High performance computing networks. So we've been able to model a large number of different computing networks. We've modeled large scale circuit simulations. So this time compression story we see over and over again across these models. So again, what does this sort of enable? Well, if we look at sort of 10 petaflop supercomputers, we should be able to model, right, which is sort of what we articulated here, model these quadrillion trillion event systems in less than 14 hours or so, 1 to 14 hours. And I think that's an amazing feat. The real caveat to all of this, again, I've been mentioning this, it assumes your network and your supercomputer is as good as what we observed on Blue Gene, and that was across the family. Unfortunately, today we've entered into a regimen where the networks just haven't kept up with the compute capability. If I look at our AMOS system as well as the Summit and Sierra systems that are available today, amazing systems, no doubt about it, but the networking is by any stretch underpowered for what the compute nodes can do. It's a 1 to 2,000 ratio where you can compute something like nearly 50 teraflops of compute on a node, but you've only got roughly about 25 gigabytes of network bandwidth. And as much as 25 gigabytes sounds like, the fact is that if you have that much compute on a node, you really need to think about, I think, a much faster, more capable network. And in fact, we're seeing that in the future exascale systems that are slated to potentially come out. There are even more rails than what we're seeing on these current systems. So again, future directions with this, again, what you can model with this is, just you can use your imagination. So we can model the whole US internet at a packet level potentially in these systems. We could look at quality of service issues. We are already looking at whole system HPC network models. So, the future machines are going to have Dragonfly networks. We've seen also fat tree networks, things like that. So a lot of network modeling capability here. On the military side, you can model their communication networks for whole theaters of war or for large sections of a particular branch of the military. So you could look at real-time active network control as an example. Even more impressive, I think, would be the ability to model the human brain, really at hundreds of billions of neurons, trillions of synapses. So there we're going to need, exa events per run, so beyond, exascale type systems. And then, of course, agent-based models for every human on Earth. And we've, a global economic model food, water, energy, and of course, obviously with COVID-19 being around, the pandemic, flu, and disease modeling. And there are folks already who are using discrete event models. We're tangentially involved in some of those activities as well, to look at, the spread models of across the world and things like that. In fact, I would say right now that, it's not so much the compute that's the hard problem anymore, given the supercomputing capabilities and the software. It's really getting a hold of the data. I think that that's where the missing piece is getting hold of the data to drive these models is probably the next big challenge in this. And I just want to finish up and say thank you for your time. And I did try to move through things a little quicker so that we had time for questions, if that's appropriate for this. And again, thank you for listening, and have a great day.
Thank you, Dr. Carothers, for the great talk. We really appreciate it. Yeah, if you have time for Q&A, say maybe a couple of students have some questions.
Sure, absolutely.
So it's if you can see the chat section, Adam doesn't have a mic, but he asked a question.
Let's see. Could you? I'm still sharing. Let me stop sharing, and then I can get to the chat.
Yeah, sure.
All right. Let me turn off sharing. Stop sharing. All right. So, and chat function. For large scaling, what other takeaways do you want to have? That's a great question. So I think, subtly under the covers for large scaling is in the p-hole model, despite it being a bit pathological, for example, and a number of the models, we have seen if your model has an incast problem, right? And by incast, I mean you get a lot of events, a few LPs sending, or a lot of LPs sending to a few LPs. That becomes a hotspot in your model, and that can sort of hurt your scaling performance, and so you have to watch for that. Now, the funny part about that story, I say, is we see networks that one of their phenomena is they do incast, and so then your model, the performance of your parallel model begins to emulate in a weird way the underlying performance problem that you're modeling in sort of a weird way. So we see those types of effects. And so if the model is actually modeling something that doesn't have a lot of parallelism to it, you're sort of stuck with that. That's the other piece of it. Sometimes maybe but you may have to think about breaking your problem down. And so I didn't talk too much about that, but I think the load balancing or proper decomposition of your problem is another important aspect to this as well, and it cannot be discounted. Let's see. Other question. I saw another one in there. Efficiency. Why did efficiency drop off so fast? So that's a great question. What was happening there is, so with time warp is somewhat of an inherently unstable scheduling algorithm. You can think of, in a physics term, trying to balance a bead of water on the head of a pin. We're sort of doing that in computation. And what we're doing is we're scheduling events in the future. And as long as we have enough work to be done per unit of time advance, we can keep the system in some form of stability, meaning rollbacks don't get to us. We get a few here or there, but on average, the system maintains some degree of stability. But if we don't have enough work, then we can have one rollback that develops into a whole cascade of rollbacks and infects the whole system very quickly. And so the system just begins to fall off the sort of, I guess in a physics term, the water bead fell off the head of the pin, and we get this cascading effect of rollbacks. So we try to limit that as much as possible. The way we in fact do that is we use memory to do that. Again, you can think of, if we thought of controlling a fire, right? You can control it by controlling the fuel to the fire, wood per se. So in our case, the fuel of fire for an optimistic simulation is memory. So we can control memory a bit, and we can control the LPs from becoming overly optimistic in the future. And that tends to dampen the cascading rollbacks. But as you saw from that curve, because we were scaling so far out, even that we were still seeing probably a pretty significant cascade. So we did see a significant drop off in performance. Again, the reason for that ultimately was we just didn't have enough work. So we had strong scaled out to where we were subdividing the work, the amount of number of LPs mapped to each of those MPI ranks. And there was so little work to be done at that scale that the cores were advancing time faster than the events could arrive from the other processors, and so we got the rollbacks. So long story, but that's sort of the underpinnings of why you see that type of cascading behavior.
I have a question about KMC.
Oh, okay. I'll do my best. I'm not the KMC expert, but yeah.
So I get that you have, like, when you run it when you're running KMC in parallel, you have to send your events and your queued event list back and forth. But what? So how come you can do that without sending like the whole lattice? Like, don't you need lattice information for the whole KMC?
That's a great question. I'll be honest. So my colleagues at Lawrence Livermore are the KMC experts, but they've got an approach to it where they're not having to, I think, send the whole lattice. They're just sending updates about it, and they don't have to do it every timestamp, is my understanding, or they do it for local neighborhoods. Their one application, if I recall, was for thin film deposition. And so with thin film deposition, if I recall correctly, you only had to worry about the atoms that were very near to you, or the molecules that were relatively near to you. And so you didn't have any long range implications. And so they were able to, I think, get around because of that. But for all applications, obviously that might not be the case.
Oh, I see. So they like divided it up to make it bigger, essentially.
Yes. Yeah.
Oh, okay.
I can send you a link on that if you're interested.
Yeah, if you could, that'd be really nice. Thanks.
Look up the work of Thomas Opplstraup, Opplestraup. But I can send a link to the group.
Okay. Yeah. Okay. Thanks.
Mhm.
So this is Joel. I had a couple questions. One was so these scaling studies that you did, these were strong scaling studies?
Yeah, most were strong scaling, some were weak scaling, but I think everything I showed was probably strong scaling. So we're specifically keeping the size of the problem the same and doubling the amount of compute. So that's usually of the two the harder one to achieve.
Yeah. And then I had a question about these collective operations on the blue gene and why they're so fast. I mean, if you don't have, every single node connected to one, master node or something on the computer, how in the world can they achieve these very quick times for collective operations?
Great question. So they actually used specialized accelerating hardware. So unlike say, well, InfiniBand has this now too, but the BlueGene Q system had special accelerating hardware that allowed them to do this. Going back to BlueGene L, in fact, they actually had a dedicated tree network that allowed them to do these collective operations very fast. So
it models like the tree reduction, but in hardware.
In hardware. So and they did that. So they didn't have the dedicated networks, but they in BlueGene Q, but they would utilize the same techniques. It was one 5-dimensional torus, but it review sort of all of them. There was a sort of separate piece that mimicked the tree hardware that was there. Is my understanding. And there was a lot of offload as well, because the remember that 18th core was hanging out there on the queue, and it could help manage and do a lot of the calculation and compute and participation in the collective while the host is still possibly doing other things or other activities. The other piece to this is everybody arrived at the collective operations at about the same time. So there was no operating system or other application interference that was slowing one rank down from arriving at the collective party at the same time. That was another important aspect to it. Unfortunately, so with InfiniBand, we see pretty good scaling, but because I think the delays, the wire delays, everything, it's sort of a different style of network. It's more of a cluster, compute cluster kind of network. It's fast, but probably in some cases has more bandwidth per link today. So the ED or FDR and HDR network protocols have more bandwidth, but the overall latency and then the configuration from the operating system to the network is a little different. On the modern systems such as Amos today, it's running a full Red Hat stack. So the good news is Python and everything in the kitchen sink will run on the our Amos as well as Summit and Sierra like systems. But the potential downside of that is that there's more operating system interference in jobs.
Okay. Then I had a question about the balance. I know like a couple years ago, NVIDIA and IBM came out with this NVLink, and there was a lot of hype about how that was going to kind of change this problem they had with getting data in and off the cards.
Yeah.
And I've seen some scaling studies that seem to work well for like one single DGX unit or something like that. But then when they have to communicate between the different, big fat nodes, then they have a problem. So, I mean, is the problem just that you need something like NVLink to everything, or what is the?
Yeah, absolutely. So in fact, we'll see. So we recently learned this more specifically. So the from a node perspective, the secret sauce to Amos and Summit systems. So those are called AC922s. Those systems, and they're actually different than the DGX boxes in a really fundamental way. What IBM and NVIDIA created was so IBM created this thing called CAPI, and I believe it was Compute Accelerated CAP Processing Interface. You can think of it as a super high-speed PCI on steroids. And you could get amazing memory bandwidth to sort of off-chip devices, particularly the GPUs. And NVIDIA and in IBM, they ran the NVLink over CAPI. And so one of the things is that you can get very high, like order 75 gigabytes a second, I think it's to each GPU or something, from main memory back to a GPU. And that's what CAPI provided. So you really want the CAPI plus NVLink capability. If you just have NVLink, you get you get a DGX box. And so as a specific example, if you run the LinPack performance benchmark on a DGX-like box, you cannot have LinPack touch main memory at all. Your scaling will diminish precipitously. It's because all memory access from the GPU, main memory access that is, to the GPU goes over the PCI bus, which is limited to around 8 gigabytes a second, like 1/10. And so then this is where your scaling problem comes in, is that you can't really run application code that's going to be running on the GPU and using main memory very well, because you can't keep the GPUs fed. The modern Volta GPU, it's from the 32 gigabyte memory that it's on chip on a single Volta is 900 gigabytes a second. No way 8 gigabytes a second feeds that very well. It's like trying to bring data through a straw. So what you end up doing is you just load up all your GPUs with their memory, and you can share memory over the NVLink at a much higher rate, but don't touch main memory. And so then the big advantage they have is the Summit like systems have AC922s is that you can fully load up memory and you're going to get good performance. But now, Joel, to your point, once you go off that, can you get good performance? You can still get good performance, but you have to be very careful in how you're, sending messages, and you're going to want to, really structure the computation correctly to where you're probably subdividing your CPUs to really do a lot of the communication management for you while they're keeping the GPUs fed with data. And it's a very careful dance that you have to do where you're pinning all your either MPI ranks or threads to particular CPU cores and keeping everything well orchestrated. I could say we did that actually when we were running LinPack on Amos. So it's a very careful dance, but ultimately you're hitting on something that there isn't quite enough memory bandwidth and maybe even latency available within that network to sustain the compute power that's available on those nodes.
Yeah.
But in future systems, I think we'll see the network capability jump back up. But it's not to say, again, Summit and Amos, for a lot of reasons, are really amazing systems, especially if you're running any sort of the AI, ML workloads. In addition to a number of HPC workloads, we've seen pretty good scaling from LAMPS and probably in GROMACS as well. So very, very capable systems.
I also wanted to just comment that the reverse computing was very interesting because I've definitely had problems where I had to kind of roll back things when I was like integrating differential equations and stuff, and it was starting to blow up on me because I hit an instability, and so I had to roll back the computation and reduce the step size and things like that.
Oh, that's neat. That's great.
Any other questions from people?
So, I mean, I could ask you another one about KMC if you're comfortable with it.
I'll do my best.
So if you wanted to look at, like, if you cared more about your data leading up to equilibrium, like a lot of people do KMC just to look at equilibrium, and that's fine. But like, if you wanted to look up to those events, would it almost be beneficial to not run it in parallel, but just have every node run the same thing, like to the end, and then uh, look back over, or is it not worth it to do it then?
Well, so my understanding, I don't know if this is related to your question, is one of the things that they do is they find out as they're moving forward in the calculation, they do what's called user level cancellation. So as the computation's rolling along, they'll actually retract previously scheduled computations for related, I think it's related to what you're saying, and they'll change the time step effectively of what they're looking at to try to fix it up based upon what's happening in the system. And so they'll retract a bunch of events and then reschedule a bunch of events at a new timestamp based upon new information that they're getting. I think there's a way to fix that up.
I see. Because otherwise, if you don't do that, I think it ends up not being correct. I think
They have to, they're constantly retracting events and sending them back. They actually spend a lot of time in event retraction to fix things up.
Okay.
But it's not a real rollback per se, but they're just as they're going, oh, we push this event out in the future. No, we need to do it at a different time because of something we've learned, and push it out again at a different time. So there's a lot of that happening. That's the primary thing that they're doing.
Okay. Okay. No, thank you. That helps. Thank you.
Sure. I'll send you the link to their work.
Okay. Thanks.
All right. So thank you again for the talk and answering everyone's question, Dr. Carothers.
All right, very good. And thank you all for attending today, and appreciate your questions and time. And if you have any follow-up questions, you can probably find me. You can look for Chris Carothers in the computer science department of RPI and send me an email.
Yeah, thanks, Chris. There's a spreadsheet in the Dropbox folder that I shared with them that has your name and your email address on it too. So.
All right, very good. All right.
All right, thanks, Chris.